Hello everyone, welcome to the fourth video lecture on communication networks and transmission lines. In the previous lecture, we had seen an expression for characteristic impedance for a T as well as a pi network. Also, we have seen the expression for its propagation constant. Then we moved to lattice network and also derived an expression for its characteristic impedance and propagation constant. In this video lecture, we will be seeing a particular example in which we are given a short circuit and the open circuit impedances ZSC and ZOC, and then how we can draw the corresponding T network as well as the pi network. After this, we will see how to represent a T network and a pi network, provided we are given the characteristic impedance Z0 and propagation constant gamma for that particular network. Along with this, we will be doing some numerical problems as tutorial problems. So we will start with the T network. As shown. So this is the general T network that we have drawn in previous lecture. So the total series sum impedance is equal to Z1. So each of these branch impedance should be having impedance Z1 by 2, and the total shunt arm impedance is equal to Z2. So we are given the short circuit impedance ZSC and the open circuit impedance ZOC, and we will try to represent this series sum impedances and the shunt arm impedance using these short circuit impedance and open circuit impedance. So we know that short circuit impedance ZSC is equal to that impedance when we short circuit this. So it is Z1 by 2 plus Z2 parallel Z1 by 2. So we have simplified this expression in the last lecture as Z1 square by 4 plus Z1 Z2 divided by Z1 by 2 plus Z2. So this will be our question 1. Also, we know that the open circuit impedance ZOC is equal to, when we open this side, Z1 by 2 plus Z2. 1 by 2 plus Z2. So first we will try to express Z2 in terms of ZS and ZOC. So we will try to eliminate Z1 by 2 from this by writing Z1 by 2 is equal to ZOC minus Z2. Question 2. Now we'll substitute this expression for Z1 by 2 here. So what will be our ZSE? So this is from question 2. You can write Z1 square by 4 as ZOC minus Z2 square plus Z1 is 2 into ZOC minus Z2. Into Z2 divided by Z1 by 2 is again ZOC minus Z2 plus Z2. So we can cancel certain terms here. We can open this bracket. ZOC square plus Z2 square minus twice ZOC Z2 plus twice ZOC Z2 minus Z2 is twice Z2 square. Also some terms could be cancelled here itself. This also will get cancelled, this 2. And in the denominator we have ZOC. So this will be ZOC square minus Z2 square divided by ZOC. Now we can cross multiply this and write this ZOC we can bring to this side. So ZSC into ZOC is equal to ZOC square minus Z2 square. From this we can write Z2 as square root of ZOC square minus ZSC into ZOC. So when we take ZOC outside, it will be 1 minus ZSC by ZOC. So this is our Z2. So we can write the shunt arm impedance in terms of the open circuit and short circuit impedances as Z2 is equal to ZOC into square root of 1 minus ZSC by ZOC. Now what is our Z1 by 2? Z1 by 2 is given as ZOC minus Z2. So we can write Z1 by 2 is equal to ZOC minus Z2 is this one, ZOC root of 1 minus ZSC by ZOC. On simplification we can bring ZOC outside. So it will be ZOC 1 minus root of 1 minus ZSC by ZOC. So this is our Z1 by 2. Now we will take the case of a pi network. So we have our pi network as shown. So the total series of impedance is equal to Z1 and the total shunt arm impedance should be Z2. So each of these shunt arm impedance should be twice Z2. Now for easier treatment, we can represent this by its equivalent admittance network as shown. So given the impedance network, how do we draw the admittance network? So we have the total series sum impedance equal to Z1. So when we draw the admittance network, the total series sum admittance is Y1 and the total shunt arm admittance should be equal to Y2. So when the elements are in parallel, admittance is added. So what should be the admittance of each of these parallel arm? It should be equal to half of the Y2. Okay, because these two branches are in parallel. So the net admittance or the total admittance is Y2 by 2 plus Y2 by 2, which will be equal to Y2. And what is the relationship between Y and Z? Y1 is equal to 1 by Z1 and Y2 by 2 is 1 by 2Z2. Okay, so if we cancel out 2 here, we will get Y2 equal to 1 by Z2. Okay, so this is the relationship between the impedance network as well as the admittance network. Only thing, we represent the values as impedance here. Here we represent the values as admittance here. So we will examine this admittance network and write the short circuit and the open circuit admittances. So what is the short circuit admittance? YAC. That is when we short circuit this terminal, then this admittance is ruled out. So we have this admittance in parallel with this admittance. So the total admittance will be sum total of this admittance plus this plus Y1. So Y2 by 2 plus Y1. And what about open circuit admittance? So we are opening this terminal. So we have this admittance parallel with series combination of these two admittances. So when we see series, then it is treated like parallel in impedance. And when we see parallel, it is treated like series in impedance network. So this is parallel. So we write plus and these two are in series. So the net admittance is Y1 Y2 by 2 divided by Y1 plus Y2 by 2. Okay, so this on simplification we can write similar to the previous expression that we have written. So numerator will have Y2 square by 4 plus Y1 Y2. The denominator will contain this term, which is Y1 plus Y2 by 2. So we have one equation here and another equation here. First we will try to find y1 by eliminating y2 by 2. So we can rewrite this equation as y2 by 2 is equal to YAC minus y1. So now substitute this equation in the second equation. So we have the open circuit admittance YOC is equal to, so this is y2 square by 4. So it will be replaced by YAC minus y1 the whole square plus, what is y2? y2 is twice of YAC minus y1. So replace this y2 with that expression. So we have y1 into twice of YAC minus y1 divided by y1 plus YAC minus y1. We can cancel out certain terms like this. So we have YAC square plus y1 square minus 2 y1 YAC plus 2 y1 YAC minus 2 y1 square divided by, numerator we have YAC alone. So here again some terms will be cancelled out. This y1 square and this 2 will get cancelled. So on the numerator we have YAC square minus y1 square divided by YAC. So what is YOC? The open circuit admittance. YOC is equal to, okay, we can cross multiply this YAC also, so that we have YAC into YOC is equal to YAC square minus y1 square. So what do we need? We have to find y1. So y1 is equal to square root of YAC square minus YAC into YOC. By taking YAC outside of this square root, 1 minus YOC by YAC. This is our expression for y1. Now what is y2 by 2? y2 by 2 is YAC minus y1. So from 3 we can write y2 by 2 is equal to YAC minus y1. y1 is this term. YAC root of 1 minus YOC by YAC. So this on simplification we can write as y2 by 2 is equal to YAC into 1 minus root of 1 minus YOC by YAC. Okay, so we have represented the branch admittances of this pi network in terms of its open circuit and short circuit admittances YAC and YOC. We can draw the impedance matrix by taking the inverse of these admittances, and we can represent this network, the impedance network, using this relationship between Y and Z. Next, we will take up a typical example in which we are given the short circuit impedance as J150 ohm, and so this is given the open circuit impedance as minus J50 ohm. So the question is to realize the T and pi networks. So this is a straightforward question. We have already derived the expression for the branch impedances. So this is our T network. So the expression for Z1 by 2. So this is our Z1 by 2. So Z2 is equal to ZOC. Z1 by 2 is equal to ZOC to 1 minus root of 1 minus ZC by ZOC. So on substituting these values, we have minus J50 into 1 minus square root of 1 minus J150 divided by minus J50. So this on simplification you will get as J50 ohm. Also Z2 is equal to ZOC square root of 1 minus ZC by ZOC. So again substituting these values, you will get Z2 as minus J100 ohm. So we can represent this network as J50 ohm, so also J50 ohm, and Z2 is equal to minus J100 ohm. Now what about the pi network? For pi network, we can represent the series sum admittance Y1 is equal to YAC root of 1 minus YOC by YAC. So we have the pi network like this. So this is our Z1, this is 2 Z2, this is 2 Z2. So we are given the short circuit impedance. So what is the short circuit admittance? It will be 1 by J150, inverse of this, root of 1 minus, and YOC will be inverse of this, so it will be 1 by this J50 divided by YC is again 1 by J150. So take this to numerator. So we have 150 divided by 50, which is 3, and J will get cancelled. Minus sign will make this plus. So we have square root of 4, which is 2. So this will be 2 by j 150. So what is Z1? Z1 is 1 by y1, which is inverse of this. So j 150 divided by 2 is equal to j 75. So this is j 75 ohm. Now what is y2 by 2? y2 by 2 is equal to YAC into 1 minus root of 1 minus YUC by YAC. So what is this? This is 1 by j 150. How is this? Because ZAC is j 150 ohm. So YAC is inverse of this. So it is 1 by j 150 into 1 minus root of 1 minus YUC. ZAC is minus j 50. So YUC is 1 by minus j 50 divided by YAC is again 1 by j 150. So on taking this to the numerator once again, this will be 3 with a minus sign. So it is 1 plus 3 is 4. So square root of 4 is 2. So we have 1 minus 2, which is equal to minus 1. So we have minus 1 by j 150. So this is our y2 by 2. So what is 2 is a 2? It is the inverse of this. 1 by y2 by 2 is equal to minus j 150. The unit of this is ohm inverse. So our pi network will look like this. So 2 Z2 is minus j 150 ohm. This is also minus j 150 ohm. This is the network that we have obtained. So we are given the short circuit and open circuit impedances, and we have realized the network, the T network as well as the pi network. Now we will see how we can represent a T network given the characteristic impedance Z0 and the propagation constant gamma. So we have our T network. In which we have drawn the series sum impedance, total series sum impedance equal to Z1 by 2. So each of these branch impedance will be equal to Z1 by 2. Now we will represent this Z1 and Z2 in terms of its characteristic impedance Z0 and gamma. So in the previous lecture, we have derived two relationships. One is sin h gamma t for a T network is equal to Z0 T by Z2. So on cross multiplying this, you can get Z2 in terms of Z0 T as well as the sin h gamma t. So this is one relationship we can write. So Z2 could be written as Z0 T by sin h gamma t, where Z0 T is the characteristic impedance for the special T network, which we have derived as square root of Z1 Z2 into 1 plus Z1 by 4 Z2. Another relation that we have derived in the previous lecture was cos h gamma t is equal to 1 plus Z1 by 2 Z2. So we will find Z1 in terms of Z0 and gamma. So we have already written Z2 as Z0 t divided by sin h gamma t. So cos h gamma t will be equal to 1 plus Z1 by twice Z0 t by sin h gamma t. So what is Z1? On cross multiplying, we can write Z1 as, so this cos h gamma t will come here. Okay, actually we need Z1 by 2. Okay, just so we can write Z1 by 2 is equal to Z0 t by sin h gamma t into cos h gamma t minus 1. Also we need two hyperbolic relationship. One is sin h 2x is equal to 2 sin hx cos hx. Another relationship is cos h of 2x is equal to 1 plus 2 sin h square x. So we'll apply this in this equation, this relationship in this equation. One is we will replace this cos h gamma t using this expression. So we have Z0 t into, so cos h gamma t will be replaced by 1 plus 2 sin square gamma t by 2 minus 1. And we will apply the first relationship in the denominator. So sin h gamma t will be replaced by 2 sin h gamma t by 2 cos h gamma t by 2. You can cancel some terms in the numerator as well as the denominator. This 2 will get cancelled here, and 1 sin h square gamma t by 2 will get cancelled here. So what is remaining here is Z0 t and sin h gamma t by 2 in the numerator and cos h gamma t by 2 in the denominator. So sin h gamma t by 2 divided by cos h gamma t by 2, which is tan h gamma t by 2. So this is z naught t tan h gamma t by 2. So what is z1 by 2? It is actually z naught t tan h gamma t by 2. So this is z naught t tan h gamma t by 2. This one also will be z naught t tan h gamma t by 2. Now we will take the case of a pi network. So we are given the characteristic impedance Z0 and gamma. So using this, how we can represent the pi network? So we have the network as drawn. So we have the total series arm impedance is equal to Z1. The total shunt arm impedance is equal to Z2. So each of these branch impedance should be twice Z2. Now we have to represent these in terms of Z0 and gamma. So again, in the previous lecture we have derived expression for gamma pi in terms of the characteristic impedance Z0 pi. So this is Z1 by Z0 pi. This we have derived. So what is Z1? On cross multiplying we can write this as Z1 is equal to Z0 pi sin h gamma pi. Okay, so Z1 will be Z0 pi sin h gamma pi. And what is Z0 pi? It is a characteristic impedance for this pi network, this general pi network, which we had derived as square root of Z1 Z2 divided by 1 plus Z1 by 4 Z2. This we had derived. Also we had derived an expression for cos h gamma pi is equal to 1 plus Z1 by 2 Z2. So we have Z1. We have the expression for Z1 like this. So we can substitute it here to get 1 plus Z0 by sin h gamma pi divided by 2Z2. So from here what do we need? We need 2Z2. So that is already here. So we will cross multiply and write 2Z2 as Z0 pi sin h gamma pi divided by cos h gamma pi minus 1. Again we will use the previous hyperbolic relationship and substitute this as 2 sin h gamma pi by 2 cos h gamma pi by 2, and this will be replaced by 1 plus 2 sine square gamma pi by 2 minus 1. We can cancel out certain terms from the numerator as well as the denominator. This also will get cancelled. So we have z0 pi into cos h gamma pi by 2 divided by sin h gamma pi by 2. So that will be cot h gamma pi by 2. So z0 pi into cot h gamma pi by 2. So 2z2 is on the left hand side. So this is z0 pi cot h gamma pi by 2. This also will be z0 pi cot h gamma pi by 2. Now we will take up a numerical in which we are given the characteristic impedance Z0 and propagation constant gamma for a symmetrical T network. We are asked to realize the network. So we are given Z0 equals 600 ohm and gamma equals J pi by 4 for a symmetrical T network, and we are asked to realize the network. So we have the T network like this. And we have derived the branch element impedances in terms of the characteristic impedance and propagation constant. So this is Z1 by 2. So this is equal to Z0 T tan H gamma T by 2. This is also Z0 T tan H gamma T by 2. And this is Z2. So that is Z0 T divided by sin H gamma T. So the characteristic impedance is given as 600 ohm. So that is our Z0 T. So that is 600 ohm, and the gamma T is given as J pi by 4. Now we need to evaluate sin H gamma T. So what is sin H gamma T? It is e power gamma T minus e power minus gamma T divided by 2. So what is e power gamma T? Is equal to e power J pi by 4. So this is actually 1 into e power J pi by 4. We do not have e power alpha. So alpha is equal to 0. So this is e power 0 into e power J pi by 4. Because attenuation constant is not there, only phase shift is there. So this is a purely reactive network, as we have discussed in the previous lecture. So e power 0 is 1, and angle pi by 4. Okay, in radians. So this is one angle 45 degree. So we can write this as 1 angle 45 minus 1 angle minus 45 degree e power minus theta. Okay, divided by 2. So that will be equal to 1 by root 2 angle 90 degree. In terms of complex notation, so okay, so this is 1 angle 45 degree minus e power minus gamma t. So that will be 1 angle minus 45 degree divided by 2. So on simplifying, we will get this as 1 by root 2. You can do in the calculator and see in polar notation. So this could be represented in complex notation as 0.707. Okay. So this is our signage gamma. Now what is our Z2? Z2 is Z0 t by signage gamma t. So that will be equal to 600 divided by j 0.707. So that will value to be equal to minus j 848.53. Similarly, we can evaluate tangent gamma t by 2 as tangent gamma t by 2 is equal to e power gamma t by 2 minus e power minus gamma t by 2 divided by e power gamma t by 2 plus e power minus gamma t by 2. So what is this e power gamma t by 2? So the angle is divided, is halved here. So half of 45 degree, it will be 22.5 degree. So we have one angle 22.5 minus one angle minus gamma t by 2. So it should be minus 22.5 divided by 1 angle 22.5 plus 1 angle minus 22.5 degree. So on simplification, we will get this as 0.4142 angle 90 degree. So in complex notation, this will be j 0.4142. Okay. Now what is Z1 by 2? You see. Now what is Z1 by 2? It is equal to Z0 t tangent gamma t by 2. We have tangent gamma t by 2. So Z1 by 2 is equal to 600 Z0 t into j 0.4142. So this will evaluate to be equal to j 248.53 ohm. Now we have the values here, so that we can draw the equivalent T network by using these values for impedances. So we have Z1 by 2 is equal to J 248.53 ohm. This one also be Z1 by 2 is J 248.53 ohm, and this one is Z2. So Z2 is minus J 848.53 ohm. So this is our network that we have realized. Now the last topic that we are left for this lecture is realization of a lattice network in terms of its characteristic impedance Z0 and propagation constant gamma. So we have the lattice network. So the series arm impedance will label as ZA. The diagonal arms impedances as ZB. So we will try to write expressions for ZA and ZB in terms of its propagation constant Z0 and gamma. So in the previous lecture, we had derived the characteristic impedance Z0 for a lattice network in terms of ZA and ZB as square root of, that is Z0 is equal to square root of ZA into ZB. Also we have written the propagation constant gamma as tan h gamma by 2 is equal to square root of ZA by ZB. So we have two equations 1 and 2. On multiplying 1 and 2, you will get square root of ZA into ZB into root of ZA by ZB is equal to Z0 tan h gamma by 2. So we can cancel these terms. So we have square root of ZA into square root of ZA. So it is ZA on the left hand side. So we have ZA is equal to Z0 tan h gamma by 2. So ZA is equal to Z0 tan h gamma by 2. Now what if we divide these equations 1 by 2? So we have ZA square root of ZA into ZB divided by square root of ZA by ZB. And on the right hand side we have Z0 divided by tan h gamma by 2. So we can cancel these terms. So we have square root of ZB into square root of ZB. So that will be equal to ZB, which is equal to Z0 cot h gamma by 2. So this is equal to Z0 cot h gamma by 2, and this also Z0 cot h gamma by 2. Okay. So this is our lattice network representation using characteristic impedance Z0 and propagation constant gamma. So we have ZA is equal to Z0 tan h gamma by 2 and ZB is equal to Z0 cot h gamma by 2. So with this we conclude lecture number 4. So in this lecture we have seen how we can represent a T network and a pi network given the short circuit and open circuit impedances. Then we have seen how we can represent a T network as well as a pi network given its characteristic impedance and propagation constant gamma. So we have done some tutorial problems based on this. Also we have seen how we can represent a lattice network using its propagation constant Z0 and gamma. So in the next lecture we will be seeing some of the characteristic parameters of an asymmetrical network. So we will be seeing the T network and as well as the pi network and seeing its characteristic parameters.